In this video, we're going to be talking about effect size, and you're going to learn how to compute a Cohen's d. And this is kind of that new statistics that I've been talking about or mentioning this semester. This is part of it. And moving forward, a lot of researchers want to push to look at effect size rather than just significance. And so we'll be talking a little bit more about that as the semester progresses. So as mentioned previously, there are testing concerns with hypothesis. So although very commonly used, some researchers are concerned about this idea of null hypothesis testing, and one way to combat that is to look at effect size. So some of the criticism is that the tests focus on the data and the numbers that result, and not necessarily the hypothesis. Also, the idea that the importance of the significance is somewhat ignored. Sometimes significant effects are not always substantial. Is it really important? Does it really have meaning to it? So you can get significance that sometimes is extremely small and extremely meaningless. But if it's reported, people say, "Oh, there was a significant difference here," and they don't bother to look at how small that difference was. So there's this push to look at what's called effect size. So measuring effect size isn't new. It's always been around, but looking at it is now being viewed as just as important as the significant testing is. So effect size measures the absolute magnitude of a treatment, and it's independent of sample size. So we'll talk about a few different types of measurements over the semester, but the one that we're going to start out today talking about with is Cohen's d. And again, this push is sometimes called the new statistics. Although it really isn't new, it's just really a new way of looking at the results. So this is the basic formula for Cohen's d. Nothing spectacular here. We're still looking at the mean of treatment versus no treatment. So this would be your sample mean versus your population mean. So we're looking still at the difference from the mean. Here though, instead of looking at standard error, we're using standard deviation again. So it takes away that sample size influence. And based on the value that we get, we either have what we call a small effect, a medium effect, or a large effect size. So here is showing you an effect. This would be relatively small. You have a d of 0.15. This is your distribution of SAT scores before the treatment in red, and this is distribution of SAT scores after the treatment. Here we have a relatively large effect with a d of 1.0. So just to show you an example of some numbers here, let's say after treatment our scores went up by 15, we had a standard deviation of 100. That gives us this d of 0.15. Versus here we have, for ACT scores, we still have a difference of 100, but because our standard deviation is so much smaller, it ends up with a d of 1. So we have the same point difference, but because our standard deviation is so much smaller here, we end up with a much larger effect size. Now for your student-led example. So this should look familiar. It's what we've done in the previous videos for 1 and 2 tail, but now we're going to calculate the Cohen's d. So what I'd like you to do is take the formula. We have our sample mean of our treated group over our population mean that was not treated over our standard deviation. So pause the video, try calculating that Cohen's d by yourself, and then hit play again, and let's see if we did it correctly. So here's all the information that we need, and we're just going to plug it into our formula. So our mean of the treated group is 220. Our mean for the no treatment group was 200. So this is just slightly different notation than we've been using. Our standard deviation was 48. And if we plug that all into the calculator, we get Cohen's d of 0.42, which is a medium effect size. So hopefully you got that calculation correct. I think it's pretty straightforward. And go on and watch the next video.